I'm just going to collapse all our methods, Control-Shift-, and we'll just pull back and take a look at all the stuff so far this linked list can do. It can be created. It can destroy itself. It can insert data to the front or the back of itself. It can set or change a piece of data at a certain spot. It can figure out if it's empty or not. It can figure out its length. It can retrieve the data at a specific index. It can delete the front. It can delete the back. It can turn itself into the entire thing into a string. It can insert before an index and after an index, and it can delete a specific index. There are two private methods within the class that won't be available outside the class, getNode and inRange, that are helper methods and error checker methods. And if we look at our to-do list that we've done most of the stuff up here. And I'm going to focus today on a couple here that are going to kind of be the turn it into an array is actually kind of tricky to do, but I'm going to show you how we can do that. But I'm going to add a couple to this list as well. These are, for those of you who want to, again, think about this linked list and where it potentially could go. For example, there's some other data structures called stacks and queues and things like that that if you have time to learn about, or if you study post-secondary, the methods I'm going to introduce to you will be useful for that kind of stuff. And maybe something you have to code, and so might as well do them now and just have them in your library. Okay, so let's write our next method. These are going to be short. It's a public T method called front. And all this method's going to do is it's going to return the data of the first node in the list. But it's not going to remove it like deleteHead does. DeleteHead returns the node data, but it actually removes the first item. This one just simply gives you what's at the front of the list. And it's basically two lines. If it's empty, return null. Right? So if it's an empty list, there is no front. Otherwise, I return get spot 0. So we already have a get method, so that's going to be easy. So you'll often find these very simple little methods like front, which is basically just tell me what's at the front of the list. We could have done the same thing with just get 0, but sometimes you build this into a method that sort of makes the calling of it a little more natural. We're also going to write a back method, so a public T back, that basically has the exact same code. So I'm just going to steal this. Except instead of getting 0, it gets length minus 1. So those are two simple methods, front and back, that just pull in what is the first piece of data or the last piece of data in the list. We're not even going to bother testing them. I'm sure they'll work because we've already tested the get method. Okay, so very simple methods. And again, you may not see a need for these two methods at this point. But again, if your programming expands beyond, say, high school programming, then for sure this is something that you may want to look into, as you will encounter this in other areas. Now, if you remember back in the Node class, we wrote a whole bunch of really neat methods, including a bunch I said would be useful, like the toString method and stuff like that, and the destroy method. And what we're going to write is the clone method. We're going to rewrite that. So the clone method creates a linked list. It creates a clone of itself. Okay? So the linked list method clone will clone itself. And here's how it goes. You create a linked list of generic type T, we'll call it list, equals a new linked list, again, generic type T. So that's basically calling its own constructor. So it constructs itself. At the end of this method, it'll return that list. In the middle, it will fill itself up with everything that's inside the current list. To do that, we'll just run a for loop up to the length. So from 0 to the length. And all we'll do is say list, that's our other list, dot insert tail, get spot I. And really, to be more specific, we should say this dot get I, because we're really getting it from this list. So that way we can distinguish between the two lists. We have a separate list that we're looping through. So this is a separate list. Then our for loop loops through the current list, like the list that we're currently in. Then we just basically get everything from the current list and copy it into our second list and then return that, which the purpose of which was to make a clone of our current list. And that's exactly what we're doing. We are cloning our current list. Okay, so that's another little simple method that we can add into our class just in case we need it, the front, the back, and how to clone itself. Okay. Next simple little method we're going to do is a public Boolean method, so it'll return true or false, called contains. What this is basically a search. It will search to see if the data is inside the list. Does this list contain this data? So it's going to return either true or false. So this is a simple search that just says, is cat in the list? Yes. Is cat in the list? No. Like it'll just return true or false. So here's how we'll do it. We'll make a node called current equal to the head. You'll have seen this code before for me. While current is not equal to null, we're going to go into a loop. If we happen to ever get outside this loop, we will return false. So in other words, if we get through this whole while loop, that means that we've hit the null. That's when current would become null, which means we would have hit the end of the list, and we would have never found the data. All we now need to do inside the while loop is say, well, if current dot data dot equals the data passed to it, if that's true, return true. That means we found it. But we have to have one more line inside the while loop. We have to advance current to the next node by saying current equals current.next. Okay, so that will create a link to the next node to keep moving current along. And again, I'm not going to diagram this for you guys because we've already done this in, for example, the toString method and some of the other methods we've written. So the current pointer is just moving through the list, and it's really in this line right here that matters. This is where we do our comparison. That's where we actually check. Is the data that I passed to this thing equal to the data inside the current node? If it is, then it contains it. Then it exists. So that's a basic, simple search to see, is the data in there? Okay? I'm going to run a test on that one. So I'm going to go over to here, our linked list tester program. I'm going to run it once just to see what our list looks like at this point in time. So run it. Come on, run, run, run. So we've been testing a bunch of the methods. We've been deleting. We've been inserting, etc. Stephen pointed out yesterday that maybe I should have been outputting some of this stuff, so I changed some of the code around. But here we go. At this point in the testing, the list looks like this: 5, 12, 55. So what I'm going to do is just test it by doing a system out. Whoops, spout. Oh, come on, automation. You can do this. There we go. And I'm going to go list dot contains, and I know it contains a 55, so I'm going to put 55 right there. I'm going to run that, and sure enough, true. 55 is in the list. And then I'm going to do that line again and see if it contains 133, which I know is not in the list. So I'm going to run that, false. So you can see it is working. It said 55 is true. It's in the list. And 133 is false. It's not in the list. So very simple test. Seems to work. Okay. Anyone lost at this point? Good. Okay. Now, searching for data can actually take a couple different forms. This is a simple search that just returns true or false, but that may not be useful to you. So we're going to write another little search method that returns an integer. And it's just called first index of. Okay, so let's think about what that's going to do. It's going to search the list, and it's going to return the first index of that number. Because theoretically, the number or the letter or the whatever could exist in multiple places within the list. So this will tell us where the first place it finds it. Okay? The code is very similar to the previous one. Node current equals head. However, we also need to keep a second variable going. We're going to make an index variable equal to 0. And then while current, and again, you could probably copy some of this code from the last method. Well, current's not equal to null. At the end of this loop, this time instead of returning false, we'll return -1. Remember, -1 is a number you can return when you don't find something, because that number will never actually exist, because the index always starts at 0, okay, and goes up from there. Okay, basically, again, the same code. So I'm going to steal this. If current.data equals data. Here I return index. I return the number. Okay. Then I have the same line, current equals current.next. But we have to add one more line to this. Because we are changing our index, index plus plus, our index goes up. Okay? And that's it. That's first index of. So really, it's almost identical to the previous method, except for these lines change or get added. So that's what I said. You could have basically copied and pasted the last method and then just made a couple changes. You could have added this line for index, so just add that, because now we're keeping a count because we're returning a number, not just true, false. Here we're returning -1 and not false. Here we're adding to the index so that we make sure, so that's a line we added. And then right here, we're returning index, not true. Okay? Now, what I now want you to do is copy that whole method, first index of, copy all of it, paste it, and change it from first index of to last index of. Okay, so here we just got to make a couple changes. Now, instead of searching for the first number time it occurs, we're going to look for the last one. Any ideas how you could do this? Here maybe it would be a chance for you guys to show off that you've been paying attention. Think about the linked list we have. How could I modify this code to find the last index of the data? Okay, let me give you hints. Should index start at 0? If we're going for the last index, why don't we go backwards through the list? We can do that because we have a reference to the back of the list. So instead of starting current at head, let's start it at tail. So let's make that change. So I'll mark the changes here. So that's just changed to tail. Now the index shouldn't start at 0. What should it start at? What would be the last number? Well, any way we could know that? Sure. It's length -1. So that needs to be changed. Length -1 is changed. The while loop doesn't need to change because it's now going to keep going backwards, but it'll still hit a null when it gets to the far end. This if statement won't change. It's the same. Returning index will be the same. But this line will change. What will this line change to? instead of current.next, it should be current.previous. It's now moving back. Okay? So it's not moving forwards this time. Now we're moving backwards through the list. And then, is there any other changes that we need to make? Does this line need to change? Index plus plus. Yup. Index minus minus. Right. So that should give us the last index of this value. Okay, so that's why I said copy the method and then just make those changes. Change to tail, length minus 1, previous, and minus minus. Other than that, the methods are the same. But they give you different abilities here. They give you the ability to find the first or the last index in a linked list. Okay, let's test those. Let's run a test on those. Okay, so I'm just going to run my list. So I know that my list contains 5, 12, and 55. Okay. I'm going to add or insert to the back, insert to the tail, another 5. And the reason I'm going to do that is then I'm going to print the list. So you can see here, now the list contains 2 5s. A 5 here and a 5 there. One at the front and one at the back. And I kind of don't want them to be totally at the front and back. So I'm going to actually insert a, I don't know, a 23 at the back as well. And insert to the head a, I don't know, 98. So I'm going to insert a 5, a 23, and a 98 to the front and back. So that now it looks like this. 98, 5, 12, 55, 5, 23. So I know there's 2 5s in there. Okay? So I'm going to output list dot first index of 5. So the very first time I find the 5, it's going to output that. I'm also going to output list dot last index of 5. So it should give me the first occurrence of the number 5 and the last occurrence of number 5 in the list. Let's test that. So what it says is 1. So at spot 0. Now let's see if it got it right, right? So this is our list right now. If we think of it like an array, an index like an array, it worked. Look, it found the first instance of 5 at spot 1, and the last index of 5 at spot 4. So it seems to test out well. Seems to be doing what we'd expect it to do. Okay, those are the extra methods that I said you guys could probably use. We had kind of identified one of them. We had search marked as something that we should do. We've now done the search. We've done it really well. We've done 3 different versions of the search. But I want to talk for a second about sort and saving. Okay, so we've done that now. Sorting the list is something we did a whole unit on. We did sorting already. Same with these two. We've already done this in previous units. So why bother doing it again? I can already sort and I can already save and open, but in order to do all 3 of these things, I need to do it with an array. That's what we did it in the previous examples. We sorted arrays and we saved and opened arrays. So I'm going to not bother doing these methods as long as I can maybe do these 2 methods. Because if I can turn my entire linked list into an array, then I can just use the code I already have. And if I can turn an array into this linked list, this is going to be easy. So I could theoretically, if I needed to sort the linked list, I could temporarily turn it into an array, sort the array, and then take that sorted array and turn it back into the linked list. So really, these 2 are the key. So that's what we're going to do. The problem with working with arrays and Java generics is they are a little bit tricky. They're not, let's just put it this way, generics and arrays don't get along that well. So in order to do this, we're going to have to do a little bit of a cheat. And again, I don't want to get into too much details on this, but it's all about memory allocation. But we are going to make these methods. Okay? I can make them happen. I can do the magic. So we are going to make a public T-array method called toArray that will turn the entire thing into an array. And we'll be making a public void fromArray method that takes T-array as a parameter. We're going to make these two methods. And if we can make these two methods, we're going to call it a done day. It'll be finished. We got 10 minutes. Let's do this. In order to do this, to cheat this a little bit, we're going to make use of an already built-in linked list. The linked list already exists. And here's how you do it. The problem would be we're going to have two names that conflict with each other. So we have to be very specific about our name here. We have to put java.util, that's a library within Java, .linked list. So what we're doing here is we are, instead of just putting the word linked list, because if we did that, it would make reference to ourselves. We are ourselves a linked list. So now I'm making reference to a different linked list, one within this library. And we give it generic type T. We'll say it's called list equals new. And again, we have to be specific. Java.util.linked list bracket T constructor. Okay, so let me pull back so you can see all that code. Okay, so what we have here is we have essentially made another linked list, but from a different class. So this thing list dot does not use our methods. It uses the methods that are built into the collection class linked list. So you'll notice a lot of them are the same. Like there's a clone method. They have one called clear. It's essentially the same as destroy. They have slightly different names. They have get, just like ours. They have add first instead of insert first or insert head. But it's the same basic idea. But this is a built-in linked list library. So anyways, now we just use our for loop going up to length. So we're going to loop through our current list, and we're going to say list, that's the new linked list, dot add this dot get spot I. So we get stuff from the current list, and we add it to our second list. So right now, it very much like clone, we are basically just copying everything over from our current linked list into this other linked list. But now, here's where it gets weird. Now, we make a T array that we'll just call array. And it's equal to, and here we have to make a cast to type T array. Strangely, that's what we have to do. And it's list dot toArray. So the toArray method is built within that class. And then we do a cast over, and then finally we just return that array. So that's how we can turn our entire linked list into an array. It's kind of a cheat, I'm going to be honest with you. It's a little bit of a cheat, but it's going to work. Okay? From array is a lot shorter code. So let's just wrap this up by writing from array. From array, all we need to do is first destroy the list, just in case there's something already in the list. And then we use a for loop, and we go to array.length, and we just call insert tail with array spot I. And that's it. That's all there is to it. So there's toArray, there's from array, and theoretically, if these work, then we shouldn't have a big deal dealing with these. we should be able to incorporate a lot of the code we've done in the previous units, like searching, sorting, and saving and files and stuff. Okay, let's run a test on this. The test could turn out badly, but let's just try this. So we know that this entire linked list is a linked list of type integer. So let's make a integer array. Integer array called array equals list.toArray. Okay? So in theory, this array should be filled up with the same stuff that's in the list. Let's test that with a little for loop that goes through array.length. And we will output what's in the array at spot I as we loop through this list. And I'm just going to put a little I, whoops, plus equals there. So in theory, this is just a straight for loop to loop through the array, and if the array contains everything as the list, they should be the same. And they're not. I think we need a cast here, possibly. We might need to cast this to type integer. Let's just see. Oh, no. Oh, integer array. Just see what happens. And we're crashing again. Cast exception. Okay, I was telling you that this toArray stuff is a bit tricky, so I'm gonna leave that, and we're not gonna test that. I'm gonna investigate that and see what's going on. I just want to wrap up real quick this whole unit by just flipping through, again, to show you guys just some of the stuff that I had in the notes about this. Again, I'm just going to go quick. Just to be clear about everything that we studied in this unit. Some of this I'll skip through quick because I've already looked through some of this with you guys. About the linked list. And I just wanted to zip up to where we left off because we did all this. We looked at this already in lots of different ways. But in the notes, I talk about this, okay? I talk about automatic garbage collection. I have an example of this, but again, just some of the points I wanted to get across here with this idea of linked lists is that it is using memory dynamically, okay? It is only limited by the amount of memory that the system will give a program like Java to use, which means computers with larger hard drives can store more data in a linked list because it's allocating it dynamically. And that's through the operator new. New is what gives it the new memory. Okay? Then in my notes, I have the example of a node. I have an example of a linked list. Okay? It is a simpler linked list than the one we wrote. This is just a linked list of, I think it's just integers. So it's a very simple linked list. But it uses the same techniques to implement a lot of the methods, not as many as the ones we did. And it sort of dynamically talks about the way this stuff works. But it's just in the notes. So if you need it, it's there. If you still are having trouble with this idea of moving current through the list, there's a bit of an explanation in there on how, there's a little animation I made explaining how current can go through the linked list, okay? It also has little animations about things like deleting, how you have to move around nodes and stuff like that, finding, getting, setting. All of these methods are in the notes. There's also, for those of you who might be interested, an example how you could build a linked list into a graphical user interface, in this case specifically an applet. So this graphical user interface is actually built into an applet running within a web page. So if you're interested in that, you can certainly look in my notes on how to do that. There's actually code in there on how you could build that in to the applet itself. Okay, so it's all in there if you want. I wrote that back when I used Firefox as my default browser, so there's a Firefox there. Feels like old school. Okay, I did want to talk about this real quick. A couple variations on the linked list, just in theory, okay? One way you can vary the linked list is rather than just have a head reference, a lot of linked lists use what's called a head record, which is a specific node that tracks more than just the beginning of the list, but also contains information about the list itself. So for example, it might contain things like the number of nodes in the list, which we kept in a length variable. But it could also keep the largest value in the list, which means then you would never have to do a search. It would just always be stored there, or the smallest value. So some linked lists make use of what's called the head record to just keep track of some important data about the list and then go into the list itself. Okay. Now this would obviously have to be changed. Some of the methods then, when you do an insert, would have to modify or update the head record. Okay? But again, this would be something more useful to you depending on the kind of program you're writing. The next type of linked list, which is interesting, is called a circular linked list. In a circular linked list, the last node in the list points back to the first node in the list. And I think I talked about that with you guys. Okay, so I just want to try it and just put that into a diagram here for a second. Come on there. There we go. Get to a blank one. Okay, so with a circular linked list, we've got this kind of list. It can be both singular or double. Doesn't matter. The last node in the list, instead of pointing to null, points back to the first node in the list. So that would be a singular linked list. In a doubly linked list, where we got nodes pointing backwards, the last node in the first node in the list would point over to the last node in the list. This would be called a circular doubly linked list. Okay? Tricky to say, but that's the way it works. But now I want to propose something to you that could be interesting. This structure can have a lot of use where this seems to be going round and round. And let me say this would be what the node class would look like. Class node, what? Why are you being like that? Okay, so class node, so let's see if you guys are paying attention to this, would take a node reference to next and previous. So that's like the node class we have. But what if it contained this, int x and y? What kind of circular structure would you know that connects nodes together and the last node goes back to the first node and it needs to keep track of an x, y? Well, not even a circle. No, you guys are thinking two and node connects to another node, connects to another node, connects to another node, connects to another node, connects back to the first node. Each node keeps track of an x, y value. This is the definition of a polygon, right? A polygon would be a collection of nodes that complete a circle. So that is where linked list type structures can expand even beyond sort of the linear structure that we're thinking about now. So again, that's kind of covered a little bit in the notes where it talks about the difference between circular lists and doubly linked lists like we wrote. There's diagrams in there of those. Examples of code, circular doubly linked lists like I just showed. With these, you don't necessarily need a tail node or tail reference because there is no tail. It's just a big circle. So really you only need one entry point, something like that. Now, as I said here, this could be the example of the polygon vertices. Okay? All right, and so that is it for linked lists.